occasion for me to talk. As I already mentioned, Shaheen, that this talk is quite different from the talk that I sometimes used to give, because this is like a summary of 40-some years of work in 1 hour.
Yeah, that.
So
yes,
that
yes,
is
that I could see. We could
anyway,
see that from your title.
You can see a topic here. It's
that
is what I'm trying to do. So let's go right away into so-called the systems that now all these in the picture you see that are already the material that we have covered. I mean, myself and my collaborators or other people have done other similar work. And so it's not just one kind. It's not glass forming. They are many. Some of them are not even glasses. They are, polycrystalline, and you can see polymer melts, which is already in the polymer viscoelastic regime. Is not the glass anymore. So all these things here are like ionic liquids. Some variations like plastic crystals, and they are also glass forming, but you can see variety. Metallic glasses at the bottom, and then pharmaceuticals, which is very close to glass forming material. Usually the crystallizers or glass form. Okay, so I just want to emphasize on this view graph here that it's not just talking in general, but it's specifically addressing all these material in properties which show universal features. And that is something which is most important for me to convey, whether you going to worry about my theoretical part. It's not important. That most important is that for you to get this point that they are really amazingly universal, and they are not trivial either. The universality is not just trivial, not just like, oh, the frequency dispersion or time correlation similar. Oh, not just that. If that's the case, that is not very important. And they're important, but they are not that important as far as I'm concerned. Okay, so let's bear this in mind. So let us go to my my usual thing of telling you why I'm starting this this work research in '78. Then I heard a talk by John Scher. Then I got, well, gee, he didn't talk about universality in general, but he talked about some frequency dispersions. So since I'm a solid-state physicist in condensed matter, but electron physics, or everything is to do with quantum mechanics. So I start out with this so-called coupling model in the paper published in Common Source Physics. But this approach is using semi-classical quantization of chaos. Actually, it turns out that way. I didn't realize that, but that's the one leads to now this book, which is too old now. It's already 10 years old. So there are a lot more things happened since then. But I put down since now it is 2022, 43 years gone by, there's no change. I mean, that's the same thing I done that time, well, but much developed, of course, in terms of comparison with experimental data and predictions and so on and so forth. But this book even is now no longer that, it's already too old. There are too many things happen which are very important. Since then, in the middle of that, we address ionics, which is also one important area, just ions, but they are also many body interacting systems. So that we collaborated with my colleagues, and this book I think is quite worth people to look at because it has experiment, theories, and relations. Okay, so what I wanted into 1978 was that I'm a source physicist. You look at energy level usually, and then interacting systems. The most famous one that I learned when I was in graduate school in Chicago is that, well, there's these nucleons. They're interacting, and there's a famous so-called Wigner's paper called random matrices. Actually, an Indian physicist by the name of Garg, he wrote a book on it. Anyway, what is said there is that, well, energy level distribution is universal, has this so-called GOE, you see the middle there. And to be more specific, the it's linear. It's you can see the px x, and then it's cut off by like a Gaussian. But this is linear in energy. In relaxation, the corresponding variables is frequency, and that would be always logarithmic. So you look at now the logarithmic of this left bottom one go to the right bottom one. You see the linearity in the log plot. And you see very nicely the cutoff is, well, just saying that there is some energy, high energy or time or frequency that you will not have this universality of the linearity of that. And that is generally a semi-classical quantization of any classical chaotic system, like the one on top. One is the stadium, okay? And that when a ball is bouncing back and forth, and then you can look at geodesics, and then you quantize, and you see the chaos. You know, you can never predict what happened afterwards. The other one's the torus is also the same thing. So nonlinearity in this case is just the boundary, but however, it's very general. So let me go to right away what I did in '79, and that is already just in this view graph. That is basically the idea is that the most of the system that we are dealing with, the potential in Hamiltonian is anharmonic. Very few things are harmonic in nature, and so anharmonicity, like you well know, the Leonard-Jones potential is highly anharmonic, and so anharmonic interaction leads to chaotic motion in phase space. But now we are not dealing with phase space, we're dealing with relaxation. So when relaxation means that initial motion is still regular. That is, you can see from many of these pictures, eventually you see that they're showing the actual data that there's a cutoff time called TC, which is the onset of chaos, because chaos doesn't come in right away. That you depend on the potential, the strength potential, and so after that it will be relaxation will slow down, and the result is always this so-called stretch exponential, become cooperative. You want to use the word, that's fine. So TC depends on the strength interaction. So the coupling model is basically capturing this crossover at TC. You have exponential because it's no chaos, so everything is regular, simple, and of course, the standard one is exponential, and with a relaxation time called tau zero on the left side, the blue one. On the right side, the red one, you see that you see this the stretch exponential right away. Now this is the result, but the main thing I will show you is that the bottom line, near the bottom line, when you look at the quasi-continuity at TC, you get this coupling model equation. Now this equation is most important. It generates, in my 40-some years, all the results, which is I'll show you it later. So there are two quantities, tau zero, and there's this TC, which is you know what I mean already. It's independent of temperature and pressure. It just depends on the potential, the strength of the interaction potential. N is the basically the coupling parameter, which is 1 minus n is the stretch exponent of the Kohlrausch-Williams-Watts function. Okay, so you see this connection on the right, the combination on the right, and then you would relate this to the actual tau or relaxation time of the complex interacting system you have usually observed. And that's what the meaning equation. Now there are bottom line, there are other papers that subsequently published, which is really to do with classical chaos, no longer quantized, any semi-classical quantization, but get the same result. Okay, so I'm not going through this real graph. I want to tell you that there are standard models of chaos that, like this one I show by Strogatz, we generalize it to interacting many body on the bottom. The bottom, you see the red one, we couple many together and you get exactly the result as I've done in 79. You see it on the left or the right. Either you look at linearity or log, double log. Double log means that if it's a slope 1, means that it's exponential. If it's sublinear, like the one on the right side, then you see this stretch exponential. You see the crossover there. Right? This is a very simple model, but it's a standard model of chaos. You get it. So that's why I was continuing to work on it, even though the earlier one was semi-classical quantized approach. Okay, let's look at data. Our data supporting that, I was lucky. In 93, Cobanero already did a neutron experiment. He was aware of my work, and he verified already. Now, this is the newer one, 2008. It's so clear. You see the crossover from exponential to stretch exponential. So it's really back up by this neutron scattering experiments. And the right side saying that this is a polymer, but you're looking at the local segmental relaxation, the red dots there. But later on, we look at the whole polymer, that is the chain themselves, they are entangled. There's a different interaction. There's a whole chain motion, and they are entangled. So it's a much weaker interaction, because this one is really at more or less at the segmental level. The other one's at chain level. But you see that also crossover. I just want to go ahead of that. So you see more, this is more recent. This is unliquid, BMIM, PF6, and then you see the crossover beautifully at 2 picoseconds. The early ones also at 1 or 2 picoseconds. This one is 2 picoseconds. They are similar molecular systems there. Okay, so you look at the left is simulation on the metallic alloys, nickel, zirconium, and then you see the same thing. The right side bottom is OTP simulation. You see similar things. They are all there. For the case of the metallic interaction, much stronger than van der Waals interaction. You can see the TC become 0.2 picoseconds, much shorter, and that is exactly what of the point depend on the interaction strength. Okay, now this is the one I already said. No longer you're looking at the segmental level, you're looking at the whole chain entangled interaction. And this is again neutron scattering experiment. And you see that if you do not have interaction, like very short chain, you so-called the Rouse modes. I mean, for polymer physics, people knows that. And that's the dashed line there. But it doesn't work, except the beginning. Well, unfortunately, the picture was produced in not emphasizing the log T. So, but anyway, you can see that dashed line passing through those data points on the left side. And you see that it works very well at the beginning, up to 1 nanosecond, and then no longer so, it slowed down and become again consistent to stretch exponential. Okay, let's look at it. When you semi-dilute an entangled polymer, then you see that the much weaker interaction. You put solvent there, and this is done by light scattering, no longer neutron, and you see the crossover for 2 cases, very different concentration, very clearly, and the time is now much longer, 10th of a millisecond. See, right at that millisecond range there. So everything is very general. So that means this is a summary of what just said, and the QC depends on the different on the strength action, and then it's so general. I mean, it's sort of unbelievable, clear. So that's why I continue the work on it. So again, this is just for quick summary, and then you know this equation there at the bottom, near the bottom there, that is so important for my development. Okay, so this is my calling card now. I mean, for prepare for for this conference. What I'm trying to summarize here, if you don't absorb anything from now on, because most of them are experiment anyway, but there are so many different diverse type of techniques, you may not be familiar with them or material, but this is the calling card. If you look at 1 to 6, that's is the thing I'm going to talk about, and I would get ahead of myself. This is unique to the coupling model. No other model has it. No model, no matter how important they are in various aspects of it, they are not in this collection here. Okay, so what I'm going to do is each time at each topic, I will remind you of that and show you all the data to support it and tell you what it means. First one you saw already, number 1, the crossover is very general. So the word universal is always applied to each item here. Number 2, this is the one I'm going to talk about next. That is, you saw already that this equation, but now put down the variable, like temperature, pressure, momentum transfer, neutrons carrying, and etc., etc. There are other variables that you can study, okay, like concentration, whatever, friction coefficient. And then this equation would stand again, and look at the tiny little superscript, n tau 0. I want to tell you what it means here right away. It says that this n depends only on tau 0. Okay, but this equation, as you see later, that if you have tau 0, tau alpha is determined, because you see later n only depend on the potential. So for same material, only n the so-called the coupling parameter or the Corrals exponent 1 minus n depend only on tau 0. Okay, let's go to this one right away, and then we'll go to the other one later. Okay, now this is the thing we have done at the beginning. I showed the original slide because now you can see the top right corner there. I say it's so general now, it's been verified. What is this? It tells you that if you change pressure and temperature, and when you maintain a constant tau alpha, that is, look at each of the spectra, dielectric spectra, for any one of them. You look at one of them at any particular peak frequencies or at constant tau alpha. You can change pressure and temperature as you like over broad range and the spectrum and the frequency spectrum of the so-called the alpha relaxation. This is a glass forming material, so we use the word alpha. Tau alpha is the same because the peak frequency is the same, and then you have the same dispersion. Now that's amazing. So that was discovered by my various colleagues at 2005. I'm particularly proud of it because when Mike Rowland was starting that, I told him, look, pressure is so important. Let's connect with the people in Europe, particularly Marian Paluk. He came over. I invited him over to NIL, and he worked with Mike Rowland. Well, I'm older than Mike Rowland. That's why I'm saying I'm the one who so-called the thinking about what the possibility. So, for example, many of these things were done by collaboration with the Italian group, Simone and Casalini, and then Marian and Mike, and then all these were done nicely, showing the generality. Now these are 6 material, and you see that they are amazingly same. Now you see what it means is the n value is the same. The n value is the same. Okay, so on the equation on the top right, you see that if this n is the same, and then tau alpha is constant, TC is the same, is constant anyway. So that means tau 0 is almost the same, right? Because everything is the same. TC is the same, N is the same, tau alpha, you keep it constant. That means tau 0 is also constant. So that means that's why I return it to you, to this one, the top one, second one, that N depends only on tau 0 or tau alpha. That's very important. So because I already told you for a single material, the harmonic and harmonic potential is also important, of course. But if you have the same material, then this thing verifies that. So that by now there's so many data now. This one view graph is still already old, maybe 5-6 years old, and it's already more than 60 or plus. So let's go to the bottom left, right, which is 2-1 done by Simone. Let's see now. You see that there's a beta relaxation with the arrow there. It's not that well resolved, but it's definitely a beta relaxation. Okay. And also can be verified to be the tau, to be the one, because you'll see later why. There's another one there. So all these things here are also, oh, sorry, this arrow, the light arrow is pointed the wrong way, should be on the other side. So this is 201. Okay, so now number 2 is, in a way now we are saying that the n depends only on tau 0 or tau alpha, interchangeable. You can see either way, okay, because the relation is already telling you n is important. Okay, now let's go to, okay, so now let's go to the next one. The next one is, so the next one is number 3, so-called decoupling parameter on exponentiality parameter, and is determined by the intermolecular potential and tau 0, not by entropy and volume. Now that's the conclusion, which is very important. And we know entropy and volume is very important. They do change, move things, move the relaxation time. But you can see that in the top, in this, the equation on top there, there's nothing. There's no entropy and volume enter, because you change pressure and temperature, so big range. For example, from 0.1 megapascal to 2 megapascal, the 2 gigapascal. There's 3 orders of magnitude change in pressure, and the temperature changes to make sure you have the same tau alpha. Look how big changes it. The thermodynamic condition, entropy and volume have to change a lot. But you see the top one, they don't move, change anything at all. So that means this coupling parameter, item number 3, is determined by the intermolecular potential in tau 0, and that's the important conclusion, not by entropy and volume. In other words, thermodynamic condition is a separate issue. Don't mess around with the n here, or the Kohlrausch parameter 1 minus n. And they are at any tau alpha, fixed tau 0, they are the same. They don't care about your entropy and volume. And that is very important. Most theory would not worry about that, but that is a truth. That is the truth here. Okay, let's go on to the next one. The primitive relaxation. Primitive relaxation is the precursor of the second relaxation of a special kind. Not all second relaxations. We call it JG beta relaxation because we honor Goldstein and Johari for their work on second relaxations. But even they, at that time, do not distinguish. But we distinguish it because I have the tau 0 there, which is expected to be related to a second relaxation of a special kind, that is, have a similar property as tau 0. So this helps, this red one, this thing in my mind already in 1998 is saying would help me to discover the JG beta, the special kind we call JG beta. So instead of JG, people may be using JG all the time. They don't discover, they don't separate them from the special kind, which has this red relation there. But we do, and so but this helps to discover this one. So let's go to this number 4. So this is the pictorial picture, which you eventually will come to discuss even the shorter time process, which called the cage motion here. So you can see that a picture of alpha on the left, and then there's a bump or sometimes even better resolve, which I call JG beta now. And the idea is that this threshold count has to this relation. That is nu beta, or this frequency now, is nearly, comparable magnitude to nu zero. Okay, so let's go on to say data. This is the same as I said already. That why this is so interesting in the early days of Johari and Goldstein is that they did also this chlorobenzene in cisdecylene. Chlorobenzene, you see on the top, is a rigid molecule, has no internal motion. So, but they still see the beta relaxation. They caught my eye in 1998. I said, gee, that must be also telling me that must be true. So I studied all the second relaxation, and then got this thing. So, okay, so this summarizes. So the pre-relaxation is a precursor of JG because it is even simpler JG beta. So, but it's starting, just initiate the JG beta. But JG beta is not just a one simple relaxation, but it's comprised of increasing length scale before it reaches the alpha relaxation. So the properties of JG beta mirrors the primitive relaxation and strong relation to alpha relaxation, like the tau zero, because it's part of tau zero. Tau zero is a part of JG beta. Okay, now by now you know that the pre-relaxation from experiment is universal. JG beta is also universal. It is found in small molecules, in the plastic crystal, polymer, metallic glasses, silicon, so forth. You can read it yourself, and it's there. It's also universal. The theme is always universal. So again, this particular part is universal. Now, so let's quickly few examples. This is the ibuprofen, and so many nice work done now at Shaheen's lab with the chairman under tutelage or chairman too. So there are a lot of nice work done in beta relaxation. So on pharmaceuticals, this is a very nice one by Baracelo, and you see the tau zero is right there. The JG beta is right there, and so that's one example. Let's go to another example. This is the one Cadra and Simone did. Very nice, very beautiful work. Now it's quinodine on the left top, on the corner. You see the molecular structure is a rigid molecule too, and then you see that the beta relaxation is well resolved. And then you see on the bottom right, you see the relaxation times measured dielectrically, and you see that this is now at ambient pressure, okay? And then you see that good agreement with the tau zero by calculation by the formula there on the right top. So it verifies the tau zero tau JG relation, and now you go to the there's again old slide. I just don't want to select any new one. But the main thing is that this tau zero and tau JG relation as calculated on the top formula. That it's obeyed by many material, many confirmation. I just used just old one, but prepared by Simone. So this is just serve the purpose. Okay, so now. Look at an even more newer results, and that is the one involved the data of Blockowitz, in which they have done very beautiful work with with light scattering, the dielectric, neutron, DSC, everything. So you see on the picture on the right, they see the alpha prime beta on top, and see the beautiful spectrum from the dielectric. You can characterize the value n value, that at different temperatures, which is very broad, like n is very large. But then when you calculate, even this case here, the beta relaxation resolved, and there are two relaxations, alpha and alpha prime. One is the alpha is the one to do with the MTHF. The molecule we're studying, which is dielectrically active, and the polystyrene is not seen because it's has very small dipole moment. On the left, you see the alpha is basically the MTHF being dominated by polystyrene, and so it is a higher temperature. The alpha prime is still, you see the MTHF, but now it's so low temperature, is confined, that is frozen already, a matrix is frozen. So it still looks like almost Arrhenius temperature dependence, but it's still there, you see that. And the beta, well, so-called JG beta now, the beta JG beta, you see that it's also Arrhenius below, but there are crossovers. They change temperature at the TG of the alpha prime. Okay, the alpha is already at the gas transition. The alpha is the temperature is already very, the frequency dependence is very high. But you see the tau zero down there, and the tau zero calculated is the two black triangles there. The circles are neutron scattering data. So this picture is very nice because it shows all the spectra on the right. It shows all the data, light scattering, neutron scattering, the DSC, the dielectric, but everything is seemed to be giving us all the way to check out everything, including the tau zero, even at such a short time, is still in agreement with neutron there. Okay, so this is just one case to show. I want to show generality. This is the one that we did with Simone and many different Chinese institutions, and Vogel, Pazzaroni, Italy, Michael Vogel in Darmstadt in Germany, and then Apostle Kirisis in Greece. So this is a combination of many different aspect of data, but this data is similar to the previous one. You see alpha 1, alpha 2 instead of alpha and alpha prime, and this is hydrated myoglobin. So this is hydrated protein with hydration level 0.28, and this data, the spectrum on the right, again you see the two the spectra dielectrically, and then you see on the left side all the neutron, all the data put together. Again, similar. So again, no, claiming universality is not a fast, because you see that this hydrated myoglobin, is very different from the other case, other materials. Okay, let's go on. Again, showing now a new spectra. This is very new. You see, it's 2021, done by I wrote the paper, but that was done in 2019 by Italian group, and then using the nuclear gamma resonance time domain interferometry experiment, which is very high tech experiment done in Grenoble, and then also done in Japan too. And you see that on the left side, you see that the spectra is the Q resolve. You can, on the top left corner, you see the you can see structure factor, and so different Q, you see and different Q at high Q, you're looking at short length scale, and this technique can give you Q resolve. You see the Q 37, 24, 13. For very low Q, you see the alpha. You see the alpha there, the gray circles there, by dielectric scattering, dielectric relaxation. So the beta relaxation is the red dots by dielectric, and then you calculate primitive relaxation from dielectric experiment. You see the yellow circles there. We know that it's already good agreement with beta relaxation from dielectric measurement. But what is nice now, you have the Q resolve data from this gamma resonance. You see that there are data on the blue, the magenta, and then the green. You see the three different Q value, and the Q value on the right is show you where the red and the green is. So when you have very short Q, very small Q, very large Q, you're looking short distances. The green one, you see they are much shorter time. So that tells you that the JG beta relaxation is a spectrum. It's by itself, and then the tau zero is just hitting it. It's just telling you, hey, I can mark where it is by this yellow highlighted circles there. So this is showing that. The right side show the spectrum. This is 5M2H. Is a mono hydroxy alcohol. It has a D-bi peak because, but forget a D-bi peak. They can get the alpha, which is now labeled by the red one, and on the right side, and then you see the beautiful JG resolved peak there. You see all the frequency at one temperature, 157, which is this. On the left side is the brown arrow, upward pointing arrow. On the right, you see that on now back to different Q, you see where they are. You see the spec. Now we can link the dielectric with the high-tech Q resolve beta relaxation. The three lines there show you where they are. This is spread, okay? And the approximate calculated tau F0, the frequency is also right there, okay? So this is very general, and this is I won't go too much into this one. It's just the same thing done earlier by Kanaya in Japan. You see there's polybutadiene. Okay, you see even more richer data. They have neutron, quasi-elastic neutron NSC data at 27.1 nanometer, very similar to the this gamma resonance Qs there. They're all overlapping with the tau 0 and the dielectric tau beta, which is the golden square triangles there, golden rectangles there. And then everything is in very good agreement with dielectric data on the right. Each of these arrow points to exactly at that temperature, 170 K where they are. And so, and then you on the bottom, you see the structure factor where the data were taken. Okay, so it's the same thing, it's agreement. Okay, so now we get back to this same thing again, that is verifying that the JG beta and tau and tau 0, tau beta JG and tau 0 are very much in linked together. And so, and also this picture tried to show that the JG beta is a spread of relaxation, and then be increasing in length scale until it reaches the Kohlrausch regime. Then you become the Kohlrausch function, which is the largest length scale allowed by the material. Okay, so this is no big deal. Again, we are now going to talk about the P and T combination a lot more now. So that because it's now linked with the JG beta. Look at the bottom line, and so we want to show now not only tau alpha is it's an N is invariant to pressure and temperature. We also show that tau JG beta is also true, because we already know that tau 0 and tau JG beta are very similar. So you may be true. So let us go to the experimental data. Okay, so now I'm going down to number 5 now. Number 5 is that this, so I try to do this part. Okay, again, this you've seen before. That was Cadra and Simone's data, in which you saw before quinidine in tristyrene. And then you see that the alpha on the left is no surprise. It's always the same. All the different symbols on is given. The inset on the right is different pressure temperature combination. See the one on the corner, the inset there, and you see they overlap, and that's no surprise. I show you already. Puppy number, forgot, 3 or 2, yeah. And then you go to the alpha beta, which is a JG beta. Wow, they are also the same place. Now this is no simple thing, because you never expected that, but it's true by experiment, and also predicted or consistent with the coupling model. You see the F naught, the arrow there's the calculated F naught, and of course F naught is always the same place. No matter how you change how you change pressure and temperature, because it's always obeying that equation. The single equation tells you that already. So this is, tells you the arrow is a good agreement as well as the same location. Okay, now this the right side is the beautiful work done by Shaheen when he was with us at that time at Pisa, and then you see that he had done this benzo NTR and with polystyrene, and then again the beautiful overlap of the alpha beta, and the pressure temperature combination he did is shown on the top corner there. So this is no surprise, and there are many more experiments done by other groups, including one by Marian Paluk's group there. And the left side is the one I did with Marian, and using this room temperature ionic liquid. Again, it's not on the. You can see that again, different pressure temperature, very different by 3 orders of magnitude, and they overlap the alpha and also the beta. Now this is the M double prime. It's the electric modulus because the ionic conductivity. So the alpha in this case is the main conductivity. And then the second relaxation is always there. As I mentioned to you, there's no matter what you're talking about, there's always a primitive relaxation to go with the long-term relaxation. So here again, you see the calculated F naught is the same, near the same place as the alpha, as the so-called secondary conductive relaxation, and the pressure temperature again holds very well on the inset. You see the same place. Okay. Okay, now this is another one which is done simulation, beautifully done by Bedroff, and then he take this bead necklace model of polymer, and then you see it on the left side. He can the beads are closer together. On the right, they are further together. Of course, you can change interactions. This interactions change, and then you see that different L. You can see the L that it's 1.4, which is very short distance. They are very N is very large because the then you see the red one is very broad. When you go to very far apart, like LE 1.7, which is on the right, then you see that they are much less, N value is much smaller. So this saying that there's a good illustration, strong interaction, larger N, and okay, longer separation between alpha and tau beta. But now the reason I do that because is that they do pressure temperature measurements simulation. So you can see that one atmosphere and 5,000 atmosphere. So you can see that how many orders of magnitude change, right? 3 orders of magnitude change, and they superpose. You see this THCF, the correlation function there. They calculate it, and you can see that the combinations there in 2 cases, you know, they are the same. No, alpha beta always remain the same. So this is their result, which is again it's a simulation, backs up the other one. This one I just did last year with our friends in China, and this is metallic alloy, zirconium copper, and then you see that this is again a liquid now, and you see in here on the top you have mean square displacement, which is the one there on the thicker line, and the dashed line is the non-Gaussian parameter alpha 2. All can be calculated from the simulation, and you see that there are different colors there. They are again very different. At the bottom give you the legend there. They are the same. Again, the total they overlap with each other on the left, on the right. Also, and you see also the intermediate scattering function. Again, whether you have 2 different temperatures. On the left, the temperatures is much higher. On the right, the temperature is much lower, but they still totally overlap. So this is another material, metallic alloys. Okay, so we almost come to the number 5, the central issue number 5. Number 5 is, number 5 is saying that how about different dependencies? I mean, on this TP, TV gamma, and Q. Let's talk about one of them, Q, which is the momentum transfer you do in experiment by neutron scattering. So let's do that. Oh, this is, let me do everything together now, so instead of worrying about. Okay, so here's the neutron scattering experiment on the left. It's on PIB, okay, polyisobutylene. And you see that the Q dependence measure, which is at the short time, on very short Q or large Q on the right, large Q at the bottom, you see the large Q larger than 1 means a short distance. Again, it's telling you it's a primitive relaxation. Indeed, it's Q squared, which is normal. Q squared is normal, okay? It's like Gaussian, like Q to minus 2, sorry. Q to minus 2 is normal, okay? So it is there. But then when you go to larger Q, which is longer distance, where now you're looking into the so-called the alpha relaxation, you become different. And again, this can be discussed in terms of that Q dependence, that equation. Well, without writing equation again, you see on the top, on the bottom of the top part, the tau alpha Q is proportional to tau 0 Q to 1 over 1 minus n. That's because that equation. Again, I just don't write down the TC and all that, but just give the Q dependence modification by the exponent 1 over 1 minus n. You saw that before, and then you immediately the n value is measured. For PIB, from the intermediate scattering function is 0.45 in the figure on the left corner there. And then you put in there minus 2 divided by 1 minus n, and then you immediately get the line, which is exactly what is right measure. So this is a good example to tell you that a simple measurement, a neutron scattering experiment, you can monitor the Q dependence. It shows everything as we would expect it. That is. Now this result is general. It's seen by light scattering. The left side is neutron scattering. You can do colloidal particles by Segre and Pusey. You can do semi-dilute polymer solution, as I showed before, Ren et al. They also do the Q dependence, Nystrom et al. And polymer cluster solution, they all find the same thing. In other words, they find the n value, and you put into this equation there, they verify the observed Q is exactly Q to the power minus 2 divided by 1 minus n. So this is one good example, clean example, to show you how this works. But now let's go to back here now, number 5. Now let's go to another dependence. Instead of Q, let's go to the TV gamma, right? Okay, that's a new thing done in the last 10 years, which is quite exciting. Oh, okay, I'll tell you another one. Forgot to tell you, even the Q dependence on the ionic liquid, same thing. The value observed is 2.5, the n value is 0.7, which is also deduced, so it's agreement again. So it's again so-called universal. It's ionic liquid now. It's no longer the case. So let's go talk about another variable, which is TV gamma. What is TV gamma? Is that they found out that if you have with some Hoover and Ross long time ago found out from rigorous statistical mechanics that if the repulsive potential goes as minus 3 gamma, r to minus 3 gamma is repulsive, and then the tau would automatically have, you talk about thermodynamic variable pressure and temperature, you're combining as T temperature and specific volume and V, and then raised to the same gamma. If that same gamma on top there as the repulsive potential, you will scale all the relaxation time. So that means all relaxation time have the function TV gamma. This is a rigorous result from statistical mechanics. You can consult Hoover and Ross. This is the one origin of that. But of course, we know that even as the Leonard-Jones is not purely repulsive, it's not pure repulsive, but still, let's motivate people to look at that about the real material, which is not purely repulsive. And this is the one experiment that we did together, well, with Simone's group there. You see the reference at the bottom, and then the left side is that they did all the pressure temperature combination, the left corner, top corner, and then they get all the data. I won't give the detail on the bottom figure. Then they summarily scale all the data and plot them as rho gamma t. Rho is 1/v, okay, density. So it's the same thing. Rho gamma t is same as TV gamma. So they scale everything. Alpha, beta, all collapse together. So the density scaling, you can see the right side. There's some kind of history by other people. Albert Simonesco in France, Gasolini and Roland, Frudas, Jubowski, Paluk, and myself wrote the book, wrote a chapter in the book on this issue about maybe 5-6 years ago. Okay, so we have this TV gamma business. Also, beta is the same. Depend on same rho gamma over T variable, same gamma, but different function, of course. See the bottom line, the bottom figure tells you they are all the same. They are functions of the same variable, same gamma, rho gamma T. But of course, they are different functions. They are not the same function. But this is very easy to understand why beta relaxation in the experiment do that, because tau zero at the bottom of this on the right side is telling you tau zero always have the same gamma, rho gamma T dependent, because of the equation again. Because the equation tells you that n is constant, so that's why TC is constant. That's why the same gamma. Okay, we're coming to the now another data. This is PMMA. Again, you see the very beautiful TV gamma scaling. Bottom again, T rho to the 1.94. The gamma is 1.94. So, so you see that, I already tried to explain to you, because tau zero and tau alpha relate to the top equation there. So and because tau JG and tau zero are very comparable, so that means the bottom one is always true, and that's why you have the same gamma for the beta relaxation. So I think, this is the one done with Marion, and then we have a now PDE. And that is the beta is not resolved. The reason I want to show it to you, in this case, even if you don't resolve, is the excess wing, but you still have that like a unresolved JG beta, and they do scale. You would look at the tau zero, which is the one on the top left. They all scale with TV gamma, which is not surprising, of course. But the nice thing about it, the beta is always the same thing, which is also on the right. You can also express in terms of TV gamma. So that's on the bottom right here. Gamma is 4.4. Okay, so let us go one more. Okay, so these are nice, very nice data on the pharmaceuticals, and that's just ketoprofen. And so you see data from Carolina in Paluk's group. He's independent, she's independent. Then you see that isoconal superposition on the left, okay, with different pressure temperature, and they know that they can use a PVT. They using the thermodynamic, and they can scale everything back to TV gamma or rho gamma over T on the right side. And the alpha, the beta, the JG beta is not, it's only a shoulder, but it's there. So they on the right side, they scale everything and become superposed and very nicely done by as a both the alpha and the JG beta have the same function and the same dependence on the same variable, rho TV gamma. Okay, this is done at by Michela Romanini and the collaborators in Tamarit's group, and this is strongly hydrogen bonded ternidazole drug, and that formula is very complicated. It's right there. And again, a similar thing they did with pressure, temperature, and now this is ambient. This is ambient pressure, 10 to minus 4 gigapascal. And data are shown alpha, beta, and gamma. Forget about the gamma, has no consequence. And they compare with the coupling model, it's right there. You see on the left side, the figures there. And they go to 0.4 gigapascal. Now it's 0.4 gigapascal. Up there is 10 to the minus 4 gigapascal. This is 0.4. The temperatures have to be higher to get the alpha. But again, the same beta alpha relation is maintained, as well as the coupling model relation. So now they also do TV gamma on the right. Having that done, you see that they all collapses to alpha and the beta with the same gamma equal to 2 in this case. Meanwhile, see the gamma, the so-called fast gamma relaxation does not superpose whatsoever. Yeah. So you can see the difference between JG beta and gamma. Okay, now now you go to understand better what is going on. This is the way to understand it. So you usually, as I said, on the right side, your repulsive potential, like the right side on the top, then you have the rigorous result by Hoover and Ross that is always, the tau is always a function of TV gamma. Always, and gamma is only 1/3 of the M at the bottom. You see the bottom, M equal 3 gamma. Always the case. This is rigorous. Now, we know that is not the case. The left side is a Leonard-Jones, which is common from van der Waals interactions. And so you see that you have the attractive part, which is 6 raised to the power 6. And so it's not exactly so, but you may still say why it works in the previous cases. The reason is the following. That is, they do, for example, simulation has been done by Koslowich, and he did this with different Leonard-Jones potential. So the Leonard-Jones potential is M equal, they changed to M on the left side, the table there. He had done 8, 12, 24, 36, meanwhile maintaining 6 for the attractive part. So he vary M. So he want to see whether 1 M divided by 1 by 3, which is exactly would be the case with repulsive potential. Does it work for the case for the Leonard-Jones now with the attractive part included? So what they found is that in fact the gamma is very similar. You see that 3.4 versus 2.7, 4.8 versus 4, 9 versus 8, the 2 columns on the table there. 13 minus 2 versus 12. So you see that it's very similar for the simulation they get from the Leonard-Jones. And so that's why it's interesting. They found out on the figure on the right, look at the bottom. That's give you the actual Leonard-Jones potential with M equal 24, the line there. And then the power law, you fit the power law with 27.5, okay? You see that 27.5, you fit the power law, which is a dash line there. It fits very well over the repulsive part that's on the left side. So that means that's when, even though there's an attractive potential there, it really doesn't hurt that much, because the slope at the approximation with the power law is very similar to the actual one. But look what happened. On the top is the G of R, okay? And the G of R is, you can see that at the position where the slope is, that's m equal to 27.5, it is already, it becomes 0. That means this is so short distance that is determining the power. This is very important for us to know this, because what it means is that it has nothing to do with the alpha relaxation. The gamma has nothing to do with alpha relaxation. Actually, it has something to do with the JG or the tau zero. Now, that's very important, because this figure tells you you can never argue that gamma is related to the longer distances, because the power is occurring at the short distance, much shorter than it goes down to 0. The G of R goes down to 0 on the left. So that is very important, which will continue now to do that with another example. This is a real simulation of 1,4 polybutadiene. You see the potential. It's not so simple anymore. There's a Leonard-Jones, but you have to worry about, because of polymer, you worry about stretching, bonding. But still, you see on the bottom left, this is the potential there. The potential that obtained from there. At the potential there, at the slope there, which is the red one that give you the minus 8.5. I'll tell you why it's 0.5, because that's what they do on the simulation there. Okay, they got gamma equal to 2. I don't show you all the data to you, but they got gamma. So TV gamma with log C, they got 2.8 gamma 2.8, and that slope there over there is 8.5 divided by 3 is equal to 2.8, which is very much on the right side. So again, the slope at that position. Look at the bottom figure. Look at the abscissa. Look at the R value there. At that point, what is the R value? The slope there is about 2.4 or so, right? Look at 2.4. But look at now. Look at this G. Look at the G of R again. This figure, same. Look at the arrow on the left, 2.4. It is already, again, very short distances. Has nothing to do with long distance, cannot be gamma, cannot be related to alpha. That tells you again that the TV gamma originate from tau 0 or tau JG. It's not it's only because of the many body anharmonic and then the chaos, they generate cooperativity to the alpha. It becomes the same TV gamma for the alpha. Okay, that's very important to show. Another way of showing it is I collect as much as I can the data a few years ago about gamma. See the gamma values there on the bottom? Now there are two parameters. You may say this is related to alpha relaxation. One is the non-exponentiality parameter. One is fragility. There's no correlations. So this is the N value associated with alpha relaxation. But look, it's scattered everywhere. Both cases, there's no correlation. Different material, different symbols, color to show they're different kind, but there's hardly anything to do. So this is very important. So that means, okay. Chairman, how am I going? Am I?
Yeah. Maybe another 5 minutes time you can, another 5
okay.
minutes?
Okay,
Yeah.
5 minutes. So
Yeah,
let's quickly go to ionic conductors, which is totally Arrhenius now. No,
Yes.
Nothing, no more vocal function, nothing. You see the same thing. I do quickly now. Again, you look at this equation, you generate prefactors. On the bottom, they predict that your prefactor can be anomalous. Your activation can be anomalous because of the property 1/1 minus n, the scale the tau infinity. Okay, let's look at this material, which is energy material called oxygen things here. And you see that without going every detail here, you see the activation energy measure depends on the titanium or zirconium the different material. You can change the zirconium, the titanium concentration. You see the activation energy changes. Okay, Y changes, and the E star, as seen, is the measure, but it's very different from the what is bottom. See the bottom here, that the true entry barrier is actually 0.6. Okay, simulation by catalog is 0.6. It's not as high as E star, but when you take the N value that you measure on the left side and you scale it back to with the coupling model prediction, which is now EA should be 1 minus N E star, you get exactly the same value as expected, as the true value from the molecular dynamics simulation. So here I won't show much anymore because I'm running out of time, so I don't show this. This is the case I should tell you. This is a beautiful case in which now you see the EA on the right figure. You see the EA deduced from EA star on the showing lots of data, and you, as I show you, you do the coupling model equation, you get the tau zero. Look at the actual data. When you extrapolate to T infinity, the prefactor at the bottom, very bottom on the right side, you see tau infinity star is 10 to the minus 16.5, which is ridiculous. I mean, there's no such a prefactor like that, a 10 frequency like that. But look at the tau zero calculated, bam, it hits 10 to the minus 14. And the minus 14, you go to the right, the inset there, that's exactly measure the oxygen vibrational spectrum. So it's really verified that the tau zero has everything the truth. It's not the 10 to the minus 17, but it's exactly the one you measure. You use spectroscopy, I find. Okay, now let's go to the last topic, which is nano. Okay, left side is nano already. This is the same material. You go to thin films, you see what happened. You see that the left side by Kosaki et al. You go to the left side, the bulk at 2,000 nanometer is like the bulk, almost like the bulk. When you go up the arrow there, you go to 15 nanometer, you get a much different result. And that result, I put it back on the right side. On the right figure here is the purple square. See the purple square? And the arrow on the left is the same as the arrow on the right. So you see that it becomes tau zero. This is a very, very interesting material, yttrium stabilized zirconia. So-called this is an energy material here, and it has the same has a good prediction with nano. Let's go to nano now. Oh, I want to say plastic crystal because of beautiful work done by Tamarit, but I think he would discuss it, so I will skip it. Again, even with plastic crystal, now they are order, but they are the orientation disorder. You see that they are the alpha and the beta, and the left side here, the data show, and the calculated tau zero is similar to what they have, what they observed, the beta. Even that has a JG beta, and it's verified too. So last, now I'll skip a lot, and then I'll go to two recent results. This I'll skip. There are a lot of different polymer films. You get the same result. I skip here, and then okay, these are two new results because it's Professor Tamarit will talk maybe from his group there. This is they've done a beautiful work of confining pilocaine, another pharmaceutical, into 1 nanometer pore. Wow, very small pore, molecular seed. You see the alpha, which is the pink one, okay, on top, and then when you confine it, much faster, the relaxation time is shorter, and that's the bottom one. And see the data, you see the legend, you can do it yourself. And then you see that the coupling model can be calculated. That is the tau zero. So you see the calculator one is basically overlapping what they observe when you confine 1 nanometer. So in other words, you can force the tau alpha back to tau 0 if you limit the length scale to so small that you become nearly JG or one body or the tau 0. Okay, this is another experiment done at the Lunkenheimer's group there. I collaborate with them to explain it, and it's the same effect by now confining glycerol in 1.16 nanometer. Again, very small. You can see the tau alpha, you can see the tau 0 calculated, and the tau confined, which is basically within error, is the same thing. So again, 2 examples, plus the examples I already in polymer, which I skipped already. So now I skip again. These are polymers. I skip. These are surfaces. Again, you can do it at the surface. You can reduce the intermolecular coupling, because the surface you no longer have any important cooperativity. As the calculators, this is maybe the only one I make a comment, that is one they found after diffusing the surface. They measure surface diffusion constant is again in good agreement with the tau 0. So I will not go further. There are a lot more results. These are ultra stable glasses, which I will skip. Now let's go down to almost the end, which is the cage dynamics, which I will skip. And because now you see the JG and the cage dynamics are linked together in this cartoon. And so what it means is that at short times, molecules are caged. They are not moving, able to move away to even make any relaxation diffusion except seeing the anharmonic potential. But when the first tau 0 or JG moves, then the cage starts to decay. Okay, so this is I only show one view graph. The rest I will not show it. And this is colloidal particles. And this is very nice because you see that the right side at 500 milliseconds by colloidal, by confocal microscopy. You see it by eyes in the computer, of course. They see that the first jiggling motion, the first jump is the 500 seconds. You see the mean square displacement here on the main figure, 500 milliseconds is right there, okay? And that's exactly where the so-called cage dynamics, when the slope is 0.13, which is very, very small, and start within a factor of 2 or so, it become now the first hop. And the rest now, at the top now, are more hops, more cooperativity. They also do the cage dynamics measurement, and 500 on the right bottom figure, you see where it start to decay. So everything like that. So one figure only to show. I show, of course, the one I do with Shaheen. so this the one, the neutron scattering isopropyl benzene. You see the mean square displacement have 2 cuts. It's the first one is the JG beta. This is exactly the JG beta of so-called gas transition temperature. At that point, the beta relaxation frozen. So that's exactly the point. You cannot have any of these effects there, and so you see the break there. So I won't go to detail, but you see the figure, you see the reference there. Okay, there are a lot more data. Okay, I mean, I'm just trying to show universality, right? I got to tell you universality. Toluene polymers, okay, and then trehalose, sucrose, sugars, always have this effect of that beta JGB relaxation terminates the cage dynamics. The cage dynamics always become terminated. They no longer cage. That's why the JG. Okay, now we are at the end. Okay, I won't show this more. I mean, but this is showing that just one comment. You know, breakdown of Stokes-Einstein relation have been a hot subject 20-some years ago. Okay, everybody think the reason is due to that is because, oh, they have 1 over tau versus 1 over tau, because that's a beautiful belief. They think is the case. It's to do with spatial heterogeneous dynamics. So because heterogeneous, then you have to, there 1 over tau average is still 1 over tau. It doesn't work because Ranko Richard, who will talk, he is the one who showed that this doesn't work because the dispersion on the bottom left, he did the dielectric, doesn't change. You know, if dynamic heterogeneity is the cause, it has to change. It doesn't change. But the bottom figure show his data. So this he basically destroyed the idea. So that now this is admitted by the review article Adrian and Harrowell. On the bottom highlighted, you see that they agree now. But this view is now seen as inconsistent experiment and simulation. Okay, so they have to abandon the top spatial heterogeneous dynamic. Okay, this is my last view graph, of course. Okay, I provided my explanation, which is usually ignored, but anyway, now it becomes the only one can explain it. And it's a coupling model. There are two different dynamic quantities. Diffusion and viscosity are different correlation functions. They have different coupling parameter, which is reasonable. Why should they have the same? So you have that based on coupling model in the 1999 paper you can consult. I already able to explain that already. Of course, it's ignored because it's much popular to do with dynamic heterogeneity. But now they fade away. So this may be okay. So now I'm saying that this is the one. I won't go there. So now, so finally, okay, skip. That's the last one. So let me go back my calling card. This is it. So the last one, number 7, I try to warn people, you may love dynamic heterogeneity, you may love fragility. I have one figure showing the fragility. I'm not trying to discredit. I'm actually one of the co-author of the paper, which is cited more than 2,000 times on fragility. But I'm saying that these are nice phenomena, but don't lean on it. Don't depend on it because they have no impact on the properties and on tau alpha as explained from 1 to 6. So with this calling card, which I hope you will get it, and even you forget all the rest experiment anyway. As I told you, most of this experiment just giving you a very sample of them. There's a lot more, but the main thing is that you remember this calling card. You remember the coupling model. Thank you.
Thank you for your nice presentations. And this some couple of questions can be there. Another 5 minutes time. I have one question. Are you able to hear me, sir?
Yeah. Yes. Yeah.
Your coupling model, there is a TC, we are using it.
Yes.
And it is originated from the many-body interaction potential.
Yes.
But what is the range for this tau TC? The potential
TC
variation can bring a lot of changes in the tau C time. There is a possibility that we can expect that tau C can be wider range. But your time variation seems to be limited to 1 to 2 picoseconds.
No. If you go back to the earlier ones,
Okay.
no. I told you, I think
you can go up to 10 to minus 4 seconds somewhere you have shown.
No, I mean that for metallic glasses, interaction, right. It goes to 0.2 picoseconds. When you go to cases like what's that? The case of entangled polymers, which are long chain tangled together, it has the value of 1 nanoseconds. When you go to dilute it, you go to microseconds. When you go further down to colloids and things like that, they are about. I think I already passed it.
Yeah, you just passed it already. Yes.
Yeah, you can see it.
This is 10 to minus 4 seconds. Okay.
So it's the weaker.
Then the nature of potential will be your potential dependent. The nature of the potential will be completely different here.
Oh yeah. Oh, definitely, because you are now talking about different animals. For example, long chain, chain motion compared with local segmental motion is very different animals.
Yes.
So they have different experience, different potentials. Yeah.
Yes,
One
yes,
is called
completely.
entanglement coupling. The other one is called local segmental, which is almost like Len Jones in the segmental alpha relaxation of polymers. So yeah, okay. Thank you.
Okay, one more clarification. The potential, what you refer is the many-body potential or the many-body interaction, or it is something like a dipole-dipole interaction, or what is the nature of the interaction you refer for these potentials?
They are all included. It's an intermolecular potential. So
It's an intermolecular level potential.
they all include. Look at the one I showed it to you about about the 1,4-polybutadiene stimulation by the Greek group. They have all the interaction included, including the stretching and bonding and then the Leonard Jones. So all included, and they are combined to for the potential. Yeah. So they all include.
Okay, that's fine. Thank you for your answers. Any other questions, Shaheen?
It is okay. Very good presentation starting from historic till end. In your 2004 paper, you were talking about some of the JG and COSI JG samples. Some of them are not coupling model following.
Yes.
A few samples. What is the current status of those samples?
What is what? Say it again.
You wrote a paper in 2004 or 5 with Marian Palou, where you
Yes.
classified the JG relaxation.
Right.
Yeah, in some of them are still not following coupling model.
Right.
Yeah, what is your comment about? In some cases, coupling model predictions are not completely following.
Which one? Can you specify the material?
I don't remember right now, but you said that it is COSI, something like you explained in that paper.
Oh, okay. I mean, something that, well, definitely for those ones which does not go along with that are due to other effects, like the data is not clear or they do not test it. But most of it we have resolved.
Yeah, but on the other hand, we have pressure is increasing to 4 or 5 orders of magnitude. Still, the correlation between alpha and beta are excellently following. That is very interesting observation we have seen in many samples. How the thermodynamics, the many-body interaction is more predominant in those samples rather than the thermodynamic changes. That is really excellent to explain only with the coupling model. That is my comment.
Yeah, right. Thank you for comment. I think that's very nice you pointed out again. I re-emphasize to the young people, particularly who are engaging in this game. What I'm thinking about is none of these properties that I talk about in my calling card, I call it, is absent in all the theories you may read in the literature or in the past, like go back to, Adam Gibbs, three-volume theory, and the latest one of similar or maybe variation, RFOT, coupling, or whatever you were talking about. None of them are in there. They don't have JG. They don't have this pressure invariance. They do not have this. That's just Shaheen talking about. There's no such thing as this invariance of that. What do we do now? Are we going to keep on for young people? I mean, for the people who are established, they will never change. I mean, that's the way it goes. I mean, life is like this. But however, for the young people, I'm saying it's quite different. You can see it. You can examine it.
Yeah.
So what I'm saying is that you got to. I think this is what you just Shaheen pointed out. I mean, you can think about yourself. How can it how can we go on without worrying about this? That is, this pressure temperature variation over large range, you change the density by a huge amount, and entropy too, and yet the alpha relaxation is invariant.
Yes.
And then also the JG goes along with it. It also, the relation between the two are invariant to this large changes. So that means one has to be very careful being involved all the time in the pressure, in thermodynamic variables. The only thermodynamic variable is the one rules supreme. That's not true. It's actually has a separate independent effect. It's there, but it's not the central one. Okay.
Yeah. Any other questions from any audience?
Sir?
Yes.
Sir, I have a question.
Yeah,
Sir.
this is by Sapna. Yes.
Yes, sir. Sir, you have worked in ionic liquids and explained the diffusion of ions and the translational motion of ions. Like in BMIM, PFO.
I don't understand. You have to speak slower. Yeah, hopefully.
Okay. You have worked in ionic liquids and explained the diffusion of ions and
Yes.
translational motion of ions. Did you ever notice the size of ions, either cation or anion, have an influence on this?
Definitely, I'm sure that the size of ions are important, particularly ion liquids, because you can make different things. But as far as I know, that whatever the ion liquid, the number of ion liquid we have considered in the last 10 years with different people there, I have not examined exactly the trend of changes, but they all seem to no surprise. There's always this, yet whether it's resolved, totally, fully resolved or not fully resolved, that is always this so-called primitive relaxation, always accompanying the alpha relaxation. So yeah, so it would be interesting if someone, if we go back to look at very different size dependencies, as you suggest.
Yes.
But at the moment, we have not focused on that. It's just looking at each of them, and they seem to be no exception to this, what I described already. Yeah.
So I'm facing such a problem nowadays. I'm working in ibuprofen, and in last few years back, we have a combined paper on sodium ibuprofen. In that, translational or diffusion of ions has taken place. But when I replaced sodium with one bulky cation, again the dielectric behavior arose. And JG relaxation of ibuprofen is still there, but it shows some shift in the time scale, temperature scale. And the behavior is also changing. That's why I asked whether it has a dependence on the size.
Yeah, could be. Yeah, I would be interesting to consider your case more carefully. I think that those details are important, but they may lead to some interesting, more fundamental considerations. But would be only possible if if we look at it more carefully, or if you send me the results so we can then discuss about it. But at the moment here, without the detail, I would say that yeah, should be looked at, and then maybe some interesting effect may come out.
Okay, sir. Thank you.
Okay. Well, any more questions from the audience?
I would like to have one question.
Yeah, Krishna Kumar.
Hello, sir. Hello, sir. Hello, Professor. It's very interesting talk, and you consolidated most of your work, and it is very interesting. And
Thank you.
we are excited. And you mentioned, or you have shown many relation with the alpha relaxation time and the beta relaxation time, and they may have similar originality. They may have similar origin. So I have a question in terms of dielectric spectroscopy. Do you expect any interesting result regarding the strength of beta relaxation, or the relative strength of beta relaxation with alpha, based on your theoretical understanding?
You're talking about relaxation strength of the beta relaxation? Are you saying that?
Yes, del epsilon.
Sure, yeah. Well,
Yeah,
actually, I think I have a paper already about maybe 10 years ago addressing this thing here. I think the fact is this: you look at the cartoon already there. If you have, like, let me give you an example, like glycerol, that's the best example. It has very small n, n is 0.3 or so, and so it has narrow alpha relaxation, and so it has the beta relaxation, the JG beta relaxation strength is very low compared with the alpha, very low. So that's why it's not resolved. Compare, let's say, with another one. Let's say sorbitol. Sorbitol is has a longer carbon chains, and this is all the polyalcohol series. And then you have much better resolved alpha JG, much stronger. And this is all to have been answered. The reason the difference is that when you have the glycerol case, the JG is very close to the alpha from the coupling model formula. You can get it, and so it takes a long, let's say a TG. Let's call it TG. So tau alpha is 10 to the 100 seconds. The beta relaxation JG is only about maybe 2 or 3 decades or 4 away from the alpha relaxation. So to reach 100 seconds, you have to go to, and then reach about, let's say, 10 to the minus 2 seconds of the JG. You have to go a long way from vibration to the cage dynamics. So the cage dynamics has to persist a long way, from vibrational frequency, which is 10 to the 13 seconds, all the way to 10 to the minus 2 seconds of the JG beta. How many decades to go through? So this has to be very low intensity of the cage dynamics, and that leads to very low dielectric strength of the beta relaxation. On the other hand, when you have sorbitol, also a TG 100 seconds for the alpha, then beta is 10 to the minus 6 seconds. Okay, beta JG is 10 to the minus 6 seconds. You only go 6 decades from the cage dynamics to the JG. So it's much higher. The level of the cage dynamic much higher, and so subsequently the tau the JG relaxation strength is also much larger than the glycerol. So just compare sorbitol with glycerol, same 2 members of the polyalcohol series. One has 3 carbon, the other has 6 carbon, and have much different N value. And you compare with the spectrum that is from vibration all the way to alpha relaxation, going through the cage dynamics to the JG beta and to the alpha. And the paper was written. You asked Shaheen to send me the connection. I can show you the paper, and then it was explained in the way I roughly give you verbally now.
Yeah, I just have a connecting question. So if the TG is high, you expect beta will be high strength?
What is high? Say it again.
Glass transition temperature is a little higher, the glass transition temperature.
No, nothing to do with high gas transition temperature. I'm talking about the same gas transition. The same relaxation time at TG.
Oh.
I'm not talking about different gas transition time. I'm talking about glycerol at this TG, okay, which is I forgot 180, and then sorbitol is higher. But we are talking about all of them at their respective TG, and their relaxation time is 100 seconds, all at 100 seconds. Then I compare the spectrum from the vibration all the way down to the alpha relaxation through the cage dynamics to the beta relaxation. I think you probably misunderstood what I said. I'm saying that they are all different. One is to reach the beta relaxation. In the case of sorbitol, you only about maybe 6 decades. The other one you may have about 10 decades. So then, and that makes a big difference in terms of the cage dynamics, and then in turn leads to different intensity of the beta relaxation. That is the beta relaxation of glycerol is much weaker than sorbitol. That's why sorbitol is quite well resolved. In contrast, glycerol, it is not.
Thank you.
I have some
Okay.
clarification for this. What about the glycerol system?
What?
Alpha and
Sorry.
beta. Glycerol.
Yes.
Alpha and beta relaxations. And
Yeah.
what about the relaxation strength?
For glycerol,
Yeah, for a glycerol.
about what? I didn't get it.
You have
Sorry.
a beta relaxation and alpha relaxation.
Yes.
And what about the dielectric strength, del epsilon, for these two?
Well, I mean, the glycerol is the
Yes.
measurement is so clear that is the alpha is very high dielectric strength because of the polar character and the hydrogen bonding system there. But then the beta is very close by. It's not resolved. It's
Yes.
seen as the excess wing. And then only when you, like Lunkenheimer did with the long-term scaling, aging, then you start to see a little bit of like a shoulder, and showing that is the case. I don't know you people are aware of the recent paper by Blockowitz group. They're saying that this is all wrong. Instead of that, is something else. It's what they are saying about the that is to do with self-correlation and then cost. But you're not aware of that. That's okay. But turns out they are all wrong anyway.
Okay. Thank you.
So I have a doubt.
Wow.
I'm Shailaja.
Yeah.
I'm very happy to hear the talk from Ngai sir, and also I'm very happy to be here with you, sir, and with my collaborators. All the collaborators are here. I'm very happy. And I have a doubt, sir. Can you explain the relation between the refractive index and the glass transition temperature of the pharmaceuticals or any glass forming material? Is there any correlation between the refractive index and the glass transition temperature?
This part I'm not very knowledgeable on.
Typical.
Probably I know that maybe the best thing I can tell you about is that the refractive index like that are interesting. And I remember an old paper by Monahan's group there in the very long paper. They consider refractive index as a part of the discussion. That is I think it's in the very long review article in New York Academy of Science paper. I think Shaheen should know about it. That is Monahan with 10 more people.
Okay, thank you, sir.
Yeah, you can look at that paper. That would be inspiring for you.
Okay, I think Shaheen sir will share me that paper because we don't have that facility to
Okay, I'll share you.
You can share it. Okay, Shaheen, will we close it?
Yeah, of course. It is really a very nice talk, starting from a long history of glasses, and you correlated everything using your wonderful coupling model. It is really maybe Gigi sir, you can say a few comments.
That I think there are universalities. There are so many universalities we could able to see in the literature also. And I think Professor has contributed to all this sort of universality that has been established in the literature. So it's a very big contribution to the relaxation dynamics, particularly in the complex system. I think his work will go a long way for people, youngsters. And I believe that there is a lot of scope for a wonderful work based on this presentation, what he has made. It will have a very big impact on the complex system, relaxation, the complex systems. So I thank the.
Hello, excuse me, sir.
Yes.
Yeah.
Sir, I would like to read your books, but many of the books are not accessible from here. Could you please share it? It will be great pleasure for us.
So there is a request by the scholar. Your book, they would like to share it with a soft copy if it is available with you.
Oh, which book? I'm sorry.
Which book?
Ionic diffusions in some ionic liquids. I have searched it.
Right?
Yeah, ionic diffusion.
Ionic liquid book.
One published in Springer, and in which I think Ngai had described about the relation between viscosity and glass transition phenomena.
Okay. Then probably you can contact our Shaheen. Through Shaheen, we can get the copy from Professor.
Yeah, okay.
And it can be used. Okay.
Okay, sir.
That you can plan it. Okay.
No, I just want to end with one, because I'm such a hurry. I think that all these I've been doing in the last so many years would not be possible with the collaboration with so many, particularly experimentalists, and like Shai, for example, and many people I may not have mentioned in this thing here. But I think that the data speak for itself. So I say that this contribution by our particular experimentalist friends, should be the audience should take note of them instead of just saying that this is a coupling model. The coupling model turns out to be lucky in a way that everything seems to be okay, but the contribution by experimentalists are immense, and they are the one who show this thing. So, but I'm just going along with it. Okay, that's important for me to acknowledge.
Okay, thank you.
Yes, sir. I have 1 minute, sir. Because of my net interruption, I left from the meeting. And the same request is from my side also, because I need some, that is recent papers. That is, I noticed NISA's explanation, that is 2021 papers I noticed. So I request Shine sir to share this also, because it is very helpful for us.
Yeah, we can get it done.
That's not a difficult thing. Can be done. Can be done.
Okay.
Sure.
Okay, thank you.
You send your request. What are the papers you want? Probably that can be sent. Okay, so that will be done.
Okay,
Right?
sir. Okay.
Okay, I thank all the students and research scholars who gathered here and patiently. This is really a great motivation for you to take the baton forward.
Oh, I just want to. I forgot one thing to say. That I know that I respect that the power of the theoretical proudness of Indian researchers in theory. I just want to say one thing. My contribution to the theory is minimal. That is from chaos. I'm sure that in India there are a lot of young people who are very capable of making a much better theory than I can in my lifetime, at least. So I hope that this would inspire some brilliant Indian researchers, young or accomplished ones, to look into this problem, the theoretical part of it. And I wish that it would be success from the Indian side. of the research community, international community. That's my last parting word. Thank you.
Thank you, sir. Thank you, sir. Thank you for the nice
Thank you.
comment. Thank you. So we'll close the meeting now.
Yes, sir. Yes, sir. We can close
Yes.
it.
Okay, thank you. Thank you, and all.
Thank you,
Okay.
Chairman. Thank you, Chairman. Thank you, Shahi.
Thank you.
Thank you. Thank you. We'll close it. Thank you.